So, as I mentioned, the objective of today's class is to give you a practical presentation of the way I would like written assignments to be solved at the exam. Last time, which means 2 weeks ago, we had a written assignment on steel, namely a truss work, and today we're going to have a written assignment on concrete. Okay, consists of 7 points. You have them on the sheet of paper I gave you, but I sent yesterday an email. Anyway, we will go through them. What I will do now is I will draw the structure to be solved on the blackboard, then start in the solution. Okay? Turn off your cell phones, please. Mine is turned off. Okay, so this is the structure. It consists of a continuous beam spanning over 2 spans. Okay, the restraints are 1 built-in edge at the left and 2 rollers. Therefore, since the built-in edge would be enough to maintain equilibrium on the structure, we have 2 additional restraints, which means the structure is 2 times redundant. And this should guide you through the solution because it means you have to determine 2 unknown internal forces, reaction forces, whatever. Okay? That's the way to do the solution. In any case, even before starting with the solution, it is wise to think about what the solution would look like. Okay? What should we obtain? Now, as you see, there are 2 spans, one of which is loaded by means of a distributed load. The second is not loaded other than at the ends, where there are the forces the structure exchanges with the restraint at point C and with the first part of the structure at point B. Okay? So, what happens on a beam which is subjected to a distributed load? Of course, the distribution of the internal forces may vary depending on how the boundary conditions are, but I should expect in the most general case to have a parabolic bending moment and a linear shear force. Okay? So I will write here M parabolic and V linear. That's what I should expect. Okay? What happens on a beam which is not loaded? One very fast and wrong conclusion would be, well, if it's not loaded, it doesn't have internal forces. It's not like that because it exchanges, as I said, forces with the other parts of the structure, with the restraint here. So if it's unloaded, what I should expect is a linear bending moment and a constant shear force. Constant also includes, and this may happen, 0 shear force if the bending moment is constant. That I cannot tell in advance. May happen under certain conditions. Not usually in beams, in other types of elements. Then, what else could guide me through the solution? Another thing which can guide me through the solution is if I think about what the deformed shape may look like. Because the deformed shape are based on the restraints, on the position of the load, and most importantly, on the position of the contraflexure points, may guide you on the distribution, on the likely distribution of the bending moment. Okay? What will the deformed shape of such a structure look like? First of all, there are two spans. What typically happens in continuous beams is that the spans have alternate deformed shapes, which means if one goes down, the other goes up, okay? Like in a wave, okay? So either this one goes down and this goes up, or this goes up and this goes down. What is the most likely thing we should expect? If the load is placed on this span, I expect this span to go down, to deflect downwards, and this span to deflect upwards. Then, bearing in mind this, I have to look at the restraints. Here there is a clamped edge, which implies there is no displacement and no rotation. Here there is a roller, which means there is no displacement. Here there is a roller, which means there is no displacement. Finally, I should bear in mind that if this is loaded and this is not loaded, I expect this span to deflect in magnitude more than the second one. Okay? Putting all this together, one likely deformed shape is, I start with a horizontal deformed shape, then I deflect downwards, then I have to go upwards because I have to pass through this point. I will then have a rotation and go here. Something which looks like this, which tells me that at a certain point, here I will have a curvature which looks like this, here a curvature which looks like this, okay? And then the curvature from a certain point here on will look like this. And this will guide me through the distribution of the bending moments. Why? Because such a curvature originates if the bending moment is like this, okay? You can try it out, take your pencil, bend it like this, you will see a curvature like this. Here, if this is the situation, I expect the bending moment to be like this, and here again, the bending moment to be like this. So, in our sign convention, where we have positive meaning tension is at the bottom, we have negative bending moment, positive bending moment, negative bending moment. This is what I should obtain. And we'll see if we obtain it. Now, to the solution. First point says, solve the structure by means of the two standard coefficients at the back of the page. So the back of the page you have two standard coefficients. What does standard coefficient mean? It makes reference to the standard case where the beam has a length which is L and the bending stiffness which is EJ. Okay? It may not be the case. As a matter of fact, here the first case is L and EJ. The second span is 4L divided by 3 and EJ. But if you have this standard coefficient, you can get whatever coefficient you need depending on what may vary in the written assignment you have at the exam. Either the length or the bending stiffness. Okay? So, how do we solve it? What is the way to solve continuous beams? The way we always did it, either in class or when you did your practical examples with Maria Chiara during the year. We solve it by assuming unknown forces or unknown bending moments over the supports. In our case, specifically, here there is no bending moment because, as you see, the hinge is drawn like this, which means no bending moment can be transmitted. Here, on the contrary, the hinge is a half hinge, which means there can be a bending moment transmitted from the first span to the second span. So there is one unknown here and one unknown here where there is the built-in edge. Putting all this together, to solve the structure, you need to determine two bending moments which are here. One is x1, and I draw it only once because it's a moment that is exchanged between the structure and the reference system, the ground, the soil, whatever. And then there is x2 here, and I have to draw it twice because it's not an external bending moment, it's an internal bending moment, which means the bending moment which is exchanged between the left span and the right span at the center support. So it is an internal force. It has to respect the basic principle for internal forces. If there is an internal forces from A to B, there is the same internal force from B to A with an opposite sign. Okay? Or as we say, the sum of all the internal forces is 0. And then there is the externally applied load, P. So how do we solve it? You know, the conventional way to solve such a structure with these two unknowns is to separate all the causes and the corresponding effects. And specifically assuming all the unknowns to act with a unit value in order to be consistent with the standard coefficients we have. All the forces except, of course, the externally applied loads. So P is an externally applied load, it will remain P. So this means I will study the effect of the first unknown x1 with a unit value 1. This implicitly means that at the same time I consider x2 equal to 0 and p equal to 0. So the only effect acting on the structure in this case is the first unknown with a unit value. So what happens to a beam which is simply supported, hinge, with a length which is L, a bending stiffness which is EJ, when a bending moment equal to 1 is applied at one end? You look at the back of the page and you see that there are two rotations, one at the first end, one at the second end. The ratio between the two is 2. The first one is L over 3EJ, and the second is L over 6EJ. Look at the back of the page. That's the coefficient on the left. Okay? In this case, in the case of the first span, both the length and the bending stiffness are at the reference value, so we simply have to take these two coefficients as they are. Nothing has to be changed. Which means the deformed shape in this case looks like this. Here there is a rotation with one arch, two arches. This is L over 3EJ. This is L over 6EJ. Is this clear to everybody? No doubts about it, okay? No doubts whatsoever. And don't be surprised that the thing can take place across this center support. That's exactly what we want. We want to create discontinuities, and then by writing compatibility equations, we will reinstate the compatibility, which is the continuity. Okay? Same here. If there is a built-in edge, the beam should not rotate here, but we want it to rotate because with the compatibility equations we will write later, we will reinstate a 0 rotation at the first end. Okay? Second case is x2 equal to 1, meaning x1 is equal to 0 and the load is equal to 0. So what happens? One to the left, one to the right. Now, on the first span, there is nothing different from the first case we considered. It's simply mirror. Do not think and do not mistake. These coefficients are not valid only if the moment is applied to the left. They apply in the same way if the moment is applied to the right. Okay? No doubts about it. So, what happens is this. One arch, two arches, L over 3EJ, L over 6 EJ. Then, bending moment is applied also at the first end of the second span. Now, the second span is not a standard beam in terms of length and bending stiffness. I mean, the bending stiffness is EJ, but length is 4L divided by 3. So, how do we adapt these coefficients? Simply, we replace L by 4L divided by 3. That's it. So, the deformed shape looks the same, and by this I mean that the rotation at the unloaded end is half as much as the rotation at the loaded end, but this does not, you don't have to take it into account, you don't have to draw it in scale, just to tell you. Here there are 3 arches. In the standard case it would be L divided by 3 EJ, the rotation at the loaded end. Since the length is 4L divided by 3, the rotation is 4L divided by 3 times 1 over 3 EJ. By doing the math, it's 4L divided by 9 EJ. Okay? Here there is, of course, a rotation. I'm not even writing it. Why? Because I don't need it. I don't need it since... sorry. No, I will need it later on. Sorry. I will need it later on because there is point D. So I will also put the rotation here. What is the rotation here? Same way of thinking. In the standard case, this rotation would be L divided by 6 EJ. In our case, the length is 4L divided by 3. So this rotation here is 4L divided by 3 times L times 1 over 6 EJ, meaning 4L divided by 18 EJ. And I leave it like this because I want to highlight the fact that, as I said previously, as in the standard case, this rotation is half as much as this one. Standard case. This ratio between the rotations does not change if the length changes. What's the question?
Could you explain why are 3 arches?
Why?
Are 3 arches?
Just to point out the fact that this is different from this and from this. Standard convention about angles. So, this should be 4. Because again, it's different. Okay? So, of course, 2L divided by 9 EJ. Finally, external load, which means x1, x2 equal to 0. What happens when the external load applied just on the first span? Distributed load on the first span, you look at the coefficient at the back of the page, the second one, standard case, length is L, bending stiffness is VJ. So the deformed shape is symmetric with respect to midspan, which means 1 arch here, 1 arch here. This is PL over 3 to the power of 3 divided by 24 EJ. And the same happens here, PL3 divided by 24 EJ. Okay, I need them both because I need to write compatibility equations both at the first point, A, and at the center support, B. Got it? Are there any questions on all these 3 substructures that I used? Tell me. And speak up, please, because otherwise...
The far right equation,
What equation?
the 2L over 9EJ.
Yeah.
I'm just confused, just looking at some of the other assignments in a similar scenario, you didn't take that one into account.
Yeah, I mentioned that. Because if you look at point D in this assignment, it says, calculate the rotation at the right support, point C. So at a certain point, I will need it. Of course, if you know it in advance, as we do it from the beginning, also to save some time. If you don't realize, when you come to point D, you go back and you simply add this one. As a matter of fact, look at here. The rotation at point C only takes place when bending moment x2 happens. So it's easy to add it afterwards. Okay? But the question is right. Why would I add this rotation if I don't need it? Just in this case, because I know there is an assignment asking me for what happens there. Okay? So now we have to solve. We have to write the compatibility equations. How do we write the compatibility equations? We know it, we've seen it in class. Basically, at point A, where the structure is in contact with the ground, and the ground does not rotate, the reference system does not rotate, I simply have to write that the rotation at that point should be equal to 0. That's what happens if the symbol of the restraint is like that. A built-in end means no displacement, no rotation. As you see here, there is a rotation here, there is a rotation here, and there is a rotation here. These rotations cannot take place. Or, to put it in other words, the sum of these three rotations should be equal to 0. Okay? That's the essence of the force method. Force method consists in considering the structure without restraints, not without restraints, without the excess restraints, substituting the restraints with their static effects, in our case, bending moments, and then reinstating the effects of the restraints by writing compatibility equations. So, I'm going to create some space here in order to write my compatibility equations. We simply superimpose all the effects. Okay? What is the rotation here? L over 3j with x1 equal to 1. Of course, x1 is not equal to 1. x1 is an unknown value. So when I write the compatibility equation, the rotation here is x1 times L divided by 3ej. And it's a clockwise rotation. This I should bear in mind. When x2 acts on the structure, the rotation at point A is clockwise. It's equal to L over 6ej when x2 is equal to 1, meaning that in reality, the clockwise rotation at point B is equal to x2 times L over 6ej. So since they are both clockwise, there is a plus here, L divided by 6ej. Okay? Clockwise, clockwise. When the external load is applied on the structure, the rotation is again clockwise. It's PL to the power of 3 divided by 24 EJ, meaning that I complete the compatibility equation by writing plus PL to the power of 3 divided by 24 EJ, and this should be equal to 0. Do not look at the formula as it is, look at the meaning of the formula. It says there are three effects acting on the structure, 2 bending moments and 1 external load. At the first point, when I remove the restraint, they create 3 clockwise rotations, 1, 2, and 3. The sum of these 3 rotations should be equal to 0. Why? Because in reality, there is a built-in edge here. Okay? That's the meaning of the compatibility equation. I allow displacements and rotations to take place, and I set them equal to 0 at the end, because this allows me to work out the values of x1, x2, i.e. of the unknown forces. Now, let's look at what happens at the center support. When you write compatibility equations at internal points with reference to internal bending moments, you don't look at clockwise rotations and counterclockwise rotations. You look at whether the point has an angle which widens or narrows, okay? So as I used to say, this structure is flat here when there are no loads applied. I look at whether the angle opens or closes. That's the way to look at it. Another way to look at it, we've seen it in class, is to look at the relative rotation, so to set the rotation to the left equal to the rotation to the right. But that's more cumbersome, okay? So we're going to look at where the angle opens. Here there is an opening which is just L over 6EJ caused by x1 equal to 1, meaning that in reality I will put here x1 times L over 6EJ, and note that there should be always a symmetry between these coefficients. So the effect at point A of x2 is equal to the effect of the moment at point A to point B. Okay? There is a symmetry. This should be equal to this. Plus, what happens when you have x2? The angle widens, it opens by L over 3J to the left, 4L divided by 9EJ to the right. Meaning that we have L over 3EJ plus 4L divided by 9EJ. I leave it like this so you see the two contributions. Note that I sum them even if one is counterclockwise and the other is clockwise, because they both contribute to the opening in the same way, so in a positive way. That is why mark it, underline it, write it on the wall of your room, okay? Repeat it every morning when you wake up until you pass the exam, okay? Clockwise, counterclockwise only works with points that are in contact with the reference system. When you are at internal points, it doesn't work. It leads to wrong results. You're not convinced? What's the thing? You have to think about it. Yeah, think about it. But tomorrow morning when you wake up, repeat it. Okay? Plus, what happens when the external load is applied? Again, the angle widens only to the left by PL to the power of 3 divided by 24EJ. So here again, PL to the power of 3 divided by 24EJ, and this is equal to 0. Two compatibility equations, two unknowns. The problem is well posed. I can solve it and work out my two unknowns and then go on with the solution. Ask me instead of asking her. I probably know more, probably. Tell me.
I have a question of...
And speak up, please, so they can hear you at home.
Sorry.
Or on YouTube.
Just a question of the process before. Now I'm wondering, why did you multiply in the x2 equation when you were discovering the 4L divided by 9AG? Why did you multiply for 1 divided by 3AG instead of 6? Because on the graphs of the exam, shouldn't it be the delta R?
What are the graphs of the exam?
Not the graphs, but the equation of the exam in the design aids.
No. First coefficient tells you that in the standard case, at the point where the bending moment acts, the rotation is L over 3 EJ. Replace L with 4L divided by 3, 4L divided by 3 divided by 3 EJ at the loaded end where the bending moment is.
So I just have to focus if it's on the left or the opposite. If it's the
No, that's what I said previously. It's not a matter of left or right. Physics does not care about left or right. That's a convention. Physics cares about where the bending moment is.
Okay.
So, again, when you look at this coefficient, you should not look at it in the way the left rotation and the right rotation. You should look at it the rotation where the bending moment is and the rotation at the unloaded end. Okay? If you want it the other way, just put a mirror here and look in the mirror. The coefficient is still valid. Okay? So again, focus on this and also add this to the sentences you have to repeat every day when you wake up in the morning. It's not a matter of left or right. Left or right is just a convention. Okay? Okay? It's a matter of the rotation at the loaded end, the rotation at the unloaded end. Okay? And again, if you have doubts, bring a mirror with yourself to the exam. And when you have this, but the situation is reversed, put the mirror and look in the mirror. It's still valid. Got it, everybody? Okay. Now we solve. I will dedicate some more time to the solution of this system because I see that many of you have problems solving the system, and it's a pity because you have the wrong numerical solution with the correct system. So it's wise to focus on how to solve the system. If you all have this, and I presume everybody listening to the video at this point has it down on paper, I will delete it. You have it on paper. You can go back to it anytime you want. First thing I have to mention, this is not a mathematics exam, so if you have a calculator which solves systems, 2x2 systems, which means systems with two equations, you can use it. Okay? I don't care how you solve it. I simply care that you don't get it from your colleague, also because besides being a fraud, I cannot guarantee that the written assignment of your neighbor is the same as yours, okay? I sometimes change them. Maybe you didn't realize, but I do it. So careful, because if I find the solution of your neighbor in your written exam, I may have some suspicion about what you did, okay? And it sometimes happens, okay? So you can solve it by means of the calculator. If you have one, mine does it. Mine does 2x2 and also 3x3 systems. No problem. We solve it by hand, okay? Just to show that you don't need a calculator if you don't want it, or you don't need a calculator which solves systems. It's not a mandatory requirement. Also because in this case it was two unknowns. Sometimes it's only one unknown. It can happen to have only one unknown. So when you solve a system, you can solve it by substitution, which means, for example, I get x1 from the second equation and I replace x1 in the first equation. But that, in my opinion, is not the most easy way to go because it's complicated to get x1 from the second equation or x1 from the first equation because the equations have all the terms. So x1, x2, and this one, x1, x2, and this one. When you work with systems, there is a basic theorem. I don't know if it's a theorem, but it's a basic property of systems. You can replace the equations of the system with a linear combination of the equations you have. So, I call this equation A, and I call this equation B, my system is still valid if I replace either A or B with a linear combination of A and B. What is a linear combination? Basically, I can multiply the whole equation by a number and, for example, sum it or subtract it from the other equation. Now, the most smart way to go with this linear combination is to make a linear combination which gets you rid of some of the terms. For example, look at x1. x1 has a coefficient here which is twice as much as this one. So one idea is to do what? I replace one of the two equations with A minus 2B. Okay? So I multiply this equation by 2 and I subtract it from the first one. Meaning A minus 2B is what? x1, the coefficient of A stays the same, L divided by 3EJ, minus the coefficient of B multiplied by 2. What is it? Exactly L divided by 3EJ. So 2L divided by 6EJ plus x2, coefficient of A stays the same, L divided by 6EJ, minus, here the sum of this coefficient is L over 3 is 3 over 9, plus 4 over 9 is 7L over 9. Okay? Multiply it by 2, so it's 2 times 7L divided by 9EJ plus PL to the power of 3 divided by 24EJ minus this one multiplied by 2. PL to the power of 3 divided by 12EJ equals 0. Now, L divided by 3J minus 2L divided by 6J, which is again L divided by 3J, 0. Here I have x2 times a little bit of math. So here it's 6, it's 9. I have to put 18 here, AJ. So this becomes 3 minus this would be 14. So it becomes 28 when I put it to 18. Okay? Plus PL to the power of 3 divided by 24 minus PL over 3 divided by 12 is what? It's clearly minus PL3 divided by 24 EJ equal 0.
Right.
Yeah?
In the last one, why just PL and not 2PL?
Which one?
In the last of the number.
This one? No, I multiplied by 2, but multiplying this by 2 means that this becomes 12. I simplified it right away. What is 3 minus 28? It's 25. So I have x2 minus times 25L divided by 18EJ minus PL to the power of 3 divided by 24EJ equal 0. A little bit of math. L cancels out with this. EJ cancels out with this. So x2 in the end is equal to minus 18 over 25 times PL to the power of 2 divided by 24. 18 and 24 divided by 3, this is 6, this is 8. Again, I could divide it by something more. Can I? 3 and, yeah, 6, of course. 3, and this is 4. So what is left here is minus 3. 25 times 4, 100 PL squared. Okay? Are these calculations complicated? Honestly, I don't think so. It's basic math. Just have to be careful, okay? It's easier than getting x1 and replacing it in another equation, or the other way around with x2. I definitely think it's simpler. Tell me.
This rule of A minus 2B is always applicable.
No,
It's only in these cases.
of course.
Okay.
If the ratio between the first two coefficients is not 2, it doesn't work.
Okay.
Don't focus on A minus 2B. Focus on the fact that I have to work around the equations in order to get rid of something. It can be x1, it can be x2. Clearly, in the case of x2, it was more complicated to get the ratio between the two, because this is L over 6 and this is 7 divided by 9. What is the ratio between these two numbers? Weird. Okay. In the first case, it's simple. It's 2. Okay.
Professor,
Speak up.
Okay, so I understand the idea of trying to cancel out x1 to find out x2. So the second part of the calculation I understand. I don't understand the principle of subtracting one from the other. So if maybe you could repeat this again.
What do you don't
I
understand?
don't understand the principle. Why the first equation minus whatever coefficient the second equation would be equal to 0. Like I didn't understand the principle at the start.
No, it's a basic theorem. You can replace, in a system of equation, you can replace whatever equation you have in the system by means of a linear combination of the other equations or of the same equation. So don't be confused. Why is it still equal to 0? What is this minus twice this? So 0, 0. 0 minus 2 times 0, it's again 0. But the same thing I did on the first member, on the first part of the equation, has to be done to the second part. This is a basic requirement of equations.
So just math, nothing to do with the structural part, it's just
No, that's math.
okay.
As I said previously, if you have the calculator which does it, do it with the calculator. I don't care about math. Still, many of you don't have the calculator. Many of you mess everything up in this passage. So it's wise to focus a little bit on this. Now, having the value of x2, I can get x1 from which equation? Whatever. You can choose this one or you can choose this one. It's the same. I will use the first one. So, x1 times L divided by 3EJ plus, I replace minus 3 over 100 PL square for x2, 3 PL square divided by 100 times L over 6 EJ plus PL to the power of 3 divided by 24 EJ equals 0. A little bit of simplifications. EJ, 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 L, 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 and L. Now, x1 times 1 over 3 EJ plus minus 3 over 600 is basically...
It's without the EJ, you're already simplified.
Yeah, you're right. x1 over 3 minus 3pl square. It would be over 600, which means minus pl square over 200 plus pl square over 24 equal 0. I don't even know how to do it. I will use the calculator, which I don't have. In any case, the result in the end is x1 equal to minus 11pl square divided by 100. Again, simple math. We don't need to focus on how to solve this. Okay? And again, if you have the calculator which does it, do it with the calculator. Okay? My calculator does fractions as well. Do you all have calculators, or do you all use your phones? Who has a calculator? Well, some of you have. Okay. Then check, mind those fractions, so you don't even need to work around the coefficients. You simply have to put in the fractions, and the calculator does it for you. Okay? So this is our solution. We can now go on with the rest of the problem. So solve the structure by means of the two standard coefficients at the back of the page. This is point A. If you get these two values correct, you have the full points in this assignment. Depending on the mistake you do, you can get to half of the points or 0 points. Okay? If you mess all that theoretical framework of the compatibility equations, then you get 0 points. If you do a mistake in the calculations, most likely you will get half the points, provided the solution makes sense. And what means makes sense? Well, since we said how the deformed shape will look like, how it's supposed to be, I expect you to have a negative bending moment here and a negative bending moment over the center support, as I did. One is negative, the other is negative, okay? Can I now cancel? I need some space to go on. Now we have the assignment, which is determine the restraint forces, and then C is plot the diagrams of the internal forces, clearly indicate the sign conventions, which nobody does during the written exams. How do I work out the restraint forces and then go on to solve for the diagrams? What I did and what I do still now, so what I did since I was a student like you, is I break the structure in all its parts. In this case, I separate the first span from the second span. So basically, A, B, B, C. Then I mark the unknown bending moments which I just worked out. Okay? So, knowing that x1, I just deleted it, knowing that x1 is minus 11 divided by 100, I put 11 divided by 100 PL squared here. Note, I mark it with a positive sign because I know how it's acting from how this arrow is drawn. Okay? When I started solving the structure, I marked it the other way around. The solution is negative, so I reverse it. Okay? And here I have 3 divided by 100 PL squared, which acts not only here, but also here. That's the starting point, and that basically allows me to solve everything, because then what do I have? I have shear forces at the ends of the beams, and note, not what I'm saying, focus on my words. Shear forces, not restraint forces, okay? What I have on these two portions are shear forces. They may coincide with the restraint forces, they may not coincide with the restraint forces. My convention is to call this one VAB and this VBA. So basically, it's the two shear forces on span AB, one at point A, the other at point B. It's My convention, if you have another one, you're welcome to use it, provided you don't mess it up, okay? Call it F1, F2, call it A, B, call it whatever. It's a convention, this is mine, you can use it, I give it to you, but don't mess it up. So this would be called BBC, and this would be called VCB. What equations can I write to work out these shear forces? It's basic equilibrium of a beam subjected to what? To two end moments. In the case of the first span, we also have the distributed load, which, for the purpose of equilibrium only, can be replaced by its resultant force acting at midspan equal to PL. Only for the purpose of equilibrium, external equilibrium. Then when you go into internal forces, it has to become a distributed load again, okay? Got it? Because you know the distribution of the bending moment is different if you have a distributed load or a concentrated load. Whereas global equilibrium does not change, okay? You know I don't like to go with translation equations right away. I prefer to go with rotation equations. So my first equation of equilibrium will be the moment about A of AB equal 0. What contributes? The bending moments, they all contribute even if we have a bending moment right at point A. It contributes, it still contributes, okay? It's the force in A that does not contribute. So I have 11 divided by 100 PL square, counterclockwise. Then 3 divided by 100, which is clockwise. No lever arm for the two bending moments. They don't need a lever arm. They are already moments. If I'm writing a rotation equilibrium, I don't need to put anything else than the value of the two moments, okay? Then we have this load. With respect to point A, it gives a clockwise rotation. So again, it's minus, it's PL, and its lever arm is L divided by 2, so minus PL squared divided by 2. And then I have VBA, which is what I'm interested in. VBA is counterclockwise, so plus VBA times L, which is the lever arm. VBA times L equal 0. A little bit of math again. 11 minus 3 is 8 over 100. This is 50 over 100. Okay. The two have opposite signs. So in the end, the result will be VBA equal to 42 over 100 PL, which is equal to 42 divided by 2 is 21 over 50 PL. Okay? Now I will use the translation equilibrium. Because you know the translation equilibrium involves two unknowns, but now one is known. So, what does the translation equilibrium read for this? Simply, Ry equals 0, and I specify here for AB. It's VAB plus VBA minus PL equal 0. VAB, if this is 42 over 100, then this should be 58 over 100 PL, meaning 29 over 50 PL. The sum of the two gives what? The sum of the two gives PL, which is the load applied on the span. Okay? Got it? Nice.
Sorry,
Yeah.
can we just review the position of the arrows and the signs on the graph for the moment?
Here,
Yeah,
which ones?
all of them.
It's because
I assumed when I started solving my structure to have x1 like this and x2 like this. Remember?
Yes.
I found two negative values, that's why I reversed the two arrows. So I assumed the two moments to put tension at the bottom, the value is negative, so tension is at the top. Besides, it coincides with what I guessed at the beginning. This for the bending moment. For the load, there should be no doubt the load is downwards. These two forces, I simply put a sign, and the value and the sign of the solution will tell me whether I got it wrong or right. As a matter of fact, they are both positive, so I assume them to be upward. They are both positive, it means they are both upwards. Okay? So this comes from the solution. Again, this was my initial guess. I got negative values, so I reverse the arrow here and here. I have to delete them, otherwise you get confused. This is another guess. The two positive values mean I got the guess right, so they are both upwards. As I usually expect to happen when there is an external applied load which goes downwards. I expect a share of the load to go right and a share of the load to go left, okay? And I inverted left and right, but okay, you got me. Now, what happens at BC? Same. Simply, equations are simpler, and you have to be careful about what? Careful about what? The length is L for L divided by 3. Careful about this. Okay? So, let's write the equations. I will start with the moment about B of BC equals 0. What do we have? 3pl squared divided by 100 counterclockwise. I will now assume it to be negative. Why? Just to show you that conventions don't matter. Previously, counterclockwise was positive. Now I will assume counterclockwise to be negative. Why? To stress the fact that conventions do not matter. I can change them the way I want, provided I keep them within the same equations consistent. When I change the equation, I can change the convention. Okay? So minus 3pl squared divided by 100. This is counterclockwise. Nothing else other than this one, which is also counterclockwise. So minus VCB equal to 0, which means VCB is equal to, here I said careful and I was not careful, minus VCB times what? The lever arm, which is 4L divided by 3 equal 0. So VCB is equal to minus 3pl squared divided by 100 times 3 over 4L. L cancels out. So I have minus 6 divided by 40. What is minus 6 divided by 40? It's minus 3 divided by 20. Correct? What does it mean that the sign is negative?
Change.
No spoiler.
Spoiler, please.
I assumed it to be upwards. I get a negative sign.
It goes down.
When I mark the force with its correct direction, I mark it downwards.
So at the beginning of the process, I always assume all the arrows go in the same direction.
No. It's a convention. You assume whatever you want.
No, but if, for example, if I assume that the first arrow goes up and the second goes down, then the sign here is going to be negative.
So what? Are you bothered?
I don't know.
No. It's a convention, again. You assume it to be upwards, it's negative, means downwards. You assume it to be downwards, you get negative, it's upwards.
So why is it not over 100?
Because I'm stupid. That's why I do things with the calculator. Otherwise I mess it up. No, this was an error of the copy. I copied wrong. So 3 over 200, okay? Yeah, but speak up, I don't hear you.
The result is 4
Yeah.
9 over 10 400 because the multiplication.
No, you have to speak up.
9 over 400 because it's multiplication.
Oh, yes. 9 over 400. Yes. Too fast. Yeah. Let me check, because I have here not the symbolic values, I only have the numeric values. Yes, 9 over 400. So, sorry, 9 over 400. What about Ry equal Ry of BC equals 0? VBC plus VCB equal to 0 because there are no loads applied, which means VBC is equal to minus VCB, but VCB, as you see, is minus 9, which means this is 9 over 400 PL, which is quite obvious. If there are no loads applied and one force is down, the other should be up, otherwise the beam moves. So this is upwards, this is downwards. These are both upwards. I will mark the correct values. So here it's 29 over 50 PL, and this is 21 over 50 PL. And this is basically all I need to draw my internal forces diagrams, okay? Does anybody have doubts about what I did so far? Before going into the internal forces diagrams, I have to answer the question about the restraint forces. Okay? As I pointed out previously, the restraint forces are not always coincident with the internal forces. So here it's 9 over 400 PL, this shear force. Restraint forces means I have a built-in edge here, so one reaction force is like this, the other is a bending moment. Then I have the center support with just one reaction force, and then I have the last support. So, at the first end, the internal forces, since there is nothing to the left, the internal forces, which I worked out here, shear force and bending moment, they coincide with the restraint forces. There is nothing to the left, there is no other part of the structure to the left, so these internal forces are also restraint forces, which means 11 divided by 100, PL squared, and 29 divided by 50, PL, are the restraint forces at point A. At point C, which has nothing to the right, which is in direct contact with the ground, with no other interference whatsoever, this is a restraint force, so restraint force is directly 9 divided by 400 PL. You may have problems with the center support. Look here what happens. At the center support you have this shear force on the first span, this shear force on the right span. Okay? They are both upwards. You have to imagine that at the center support the situation is like this. You have the roller, you have the reaction force, which I marked here upwards. What comes from the left? If the left span is subjected to a shear force which goes upwards, it means the first span rests on the center support with a force which is downwards. Principle of action and reaction. So here you have 21 over 50 PL from first span. Can you see it? If the first span is supported by 21 over 50, it means the first span rests on the center support with this same force. You are simply looking at the same thing from two different points of view. The second span is supported by the center support by 9 over 400 PL upwards, which means it rests on the center support with a force which is 9 divided by 400 PL, which comes from second span. So in the end, how much is the restraint force? The sum of the two. Upwards. 21 over 50 is what? It's 8 per 20, 160, 168 più 9, 168 più 9, 168 più 9, 177 diviso 400. 177 divided by 400 PL. And that's the restraint force. And as you see, this restraint force is neither equal to the shear force to the left, nor to the shear force to the right. It's the sum of the two. And of course, one may ask, is it always the sum of the two shear forces? No, it depends on the sign of the shear forces. Clearly, it depends on the sign of the shear forces.
But it's always the operation between the two forces.
It's the combination. What is the difference between shear force and restraint force? When I design the beam, what is relevant is the shear force. Because at no point in the first span, at no point in the second span, there is a shear force which is equal to this one. You have to see it like this. This is the force applied. It immediately divides into two. Not half and half, but more here and less there, but it divides. So there is no point in the first span or in the second span where this force is applied. It immediately subdivides between left and right. So when I design the two portions of the beam, I use the values of the shear force. Okay? Clearly, this roller is meant to represent what? The beam resting on the ground, the column, whatever. When I design whatever is under the beam at point B, I design it with this force here. So if I'm designing, for example, a foundation under this point, the value which I use is 177 over 400, because that's the load which is acting at this point on the reference system. Got it? This point C is, no, this point it's B. It's exactly meant to see whether you have clear the difference between a restraint force and an internal force. Okay? Everybody did this drawing? You have it? Okay. We'll now delete because I want to go with the internal. No. I will drink a little bit of water. Can you hear me at home, everybody?
Yes.
Okay. One thing I forgot to mention at the beginning of the recording, of course, if I want to upload it on the YouTube channel, I was told that I need the authorization from all of you. Of course, if you appear and you're recognizable on the video, unless told otherwise, I assume that you have no problem with it, okay? Clearly the camera is pointed towards me. I won't name names, so just tell me if you have problems and I will delete the appropriate portion of the video where you appear, okay? Unless told otherwise, I assume that you're all okay with me uploading the video on YouTube, okay? And it's not because I earn money from YouTube, it's simply that I was told from other students that it's easier to access the videos from YouTube than with WebEx. So that's why I use YouTube, okay? Of course, if somebody offers me to sponsor my channel in the future, okay, I may consider that, but hasn't happened so far, so no money earned on my side. Can I delete now? Okay.
Thank you.
Now, the internal forces. Basically, again, all I need is to look at this, focusing on something which is very important. I know that Maria Chiara, during her classes, she shows you all the equations in a very detailed way in order to get the functions of the internal forces diagrams. Now, in the written assignment during the exam, it's not required that you put down all the equations. It is important that you focus on just a few points that are instrumental for drawing the whole diagram of the internal force right, okay? So we'll start with the shear force. The assignment said, read it again, plot the diagrams of the internal forces, clearly indicate the sign conventions, which means when I start drawing the diagram of the shear force, I write V. If I want to only put values, I can draw it in the scale of PL, which means I will only put numbers in the diagram, not PL all the time. Clearly indicating the sign conventions means I draw a small element of the beam with a plus, which means the positive convention. I always assume the positive convention to be shear is positive if it's clockwise. Again, not upwards, not downwards, clockwise on the portion of the beam, which means if I'm on the left end of a portion of beam, it's positive if it's upwards. If I'm on the right end of a portion of beam, it's positive if it's downwards. First span, L. Second span, 4L divided by 3. Let's immediately apply the convention. Here, what is the shear force here? 29/50. Okay? It's the left end of the first span. We are at the left. It's upwards. Left upwards means positive. (29/50). Right end of the first span, upwards, 21/50. Right end is positive if it's downwards. Since we have it upwards, this 21/50 is negative. It's a little bit smaller than this. Let's mark it like this. This is plus, this is minus, this is 21/50. How is the shear force diagram? Linear, straight line. Okay? Then, second span, left hand upwards. Left hand upwards is positive. This is 9/400. It's much smaller than this one. So I will mark it very small, not in scale, otherwise I won't see this small segment. Second end, right end of the second span, it's downwards, as is here, so it's still positive. So on the second span, we have it. Same value at both ends. In the middle, it's constant. This is all positive with a value which is 9/400. And as you see over there, I knew it from the beginning that the shear force would be constant on this span. That's what I got. Okay, no need to put down the equation of the straight line. I don't care about it. Okay? I just need the two endpoints and then I draw a straight line in the middle. Also, on the second span, knowing the shear force value at one end, I could go on constant, so drawing a rectangle from the beginning. I didn't need to put also the second value, but I did it just to make it. What is relevant again at this diagram? Well, what is relevant is the point where the shear force is 0. Why? Because where the shear force is 0, the bending moment will attain a maximum value. Where is it 0? If this is 29/50 and the load applied is P, this is 29/50 PL. Sorry, not PL, L. So, a little bit further than midspan, you have the value of shear force which is equal to 0. Now, to the bending moment, which I'm going to draw in the scale PL square. What is the sign convention? I don't put something like this. I simply specify whether I draw my bending moment diagram on the tension side or on the compression side. What we usually do in Italy, and I think all over Europe, is to draw it on the tension side. I don't care whether you draw it on the tension side, provided you specify your sign convention. So if you are accustomed to draw it on the compression side, do it, I have no problem, but please specify it. Otherwise your bending moment diagram looks reversed, and I don't understand whether you got it right or wrong, okay? Okay. So, first of all, what do we know? We know 11 divided by 100, 3 divided by 100, both negative, and then 0 here, which is a given since there is a roller. We know it from the beginning that the moment is 0 here. So, 11 divided by 100, negative, tension side, it's the top side, 3 divided by 100 here, and 0 here. So, straight ahead. The second span, the bending moment is linear. First point is here, the second is 0. In the middle, we simply have a straight line. It should look like a straight line, probably doesn't look exactly like a straight line. You may draw it better when you're during the exam because you have a ruler, you are on paper, I'm on the blackboard, okay? So forgive me if it's not a straight line, I will write it here, straight line. From 3 divided by 100 to 0. And here it's 11 divided by 100. What happens in the middle? In the middle, I have to work out the value of the bending moment here. At 29 divided by 50 PL. How do I do it? Well, I simply draw the portion of the beam starting from A with a length 29 divided by 50 L. What are the forces acting? You have the forces at point B, at point A, so 29 divided by 50 PL, and the bending moment, which is 11 divided by 100 negative. So I will simply take these two forces and draw them over there, plus the distributed load. So, on this portion of the beam, there is distributed load, there is a bending moment, which is 11 divided by 100 PL square, and there is a shear force, which is 29 divided by 50 PL. And here, what I will have is the maximum bending moment. That's the internal force I'm interested in because it's relevant for the design. Do I have a shear force here? Why don't I mark a shear force? Because this point is exactly the point where the shear force is 0. Okay? So by writing equilibrium on this small portion of beam, I get the value of the maximum bending moment. What is it? M max, which is counterclockwise, plus 11 divided by 100 PL square, which is counterclockwise, plus the contribution of the load. What is the contribution of the load? Careful. The resultant force is P distributed over a length of 2950. So it's 29 over 50 PL. The distance is what? The distance is half of 29 divided by 50. How much is half of 29 divided by 50? 29 divided by 100. So what I have here is plus 29 divided by 50 PL times 29 divided by 100 L. This is the contribution of the distributed load. And then I have the contribution of the shear force, which is clockwise. So it's negative. Minus 29 divided by 50 PL times 29 divided by 50 L equal 0. Sorry, the equation is a little bit messed up. Okay? So in the end, the result is M max equal to 29 divided by 50 times 29 divided by 50 minus its half. So this will be, how much is 29 over 29? I don't remember. $841 divided by 2500 PL square minus 841 divided by 5000, which is its half, PL square. It's the second contribution, the one of the load, okay? Minus 11 divided by 100 PL square. So the final result, I will get it for you. Everything to 5000, so 841 times 2 minus 841 minus 291. 291 over 5000 PL square. I know it's weird, but that's as good as it gets when you have all these numbers, okay? It's not a problem. Again, you do it with the calculator. In the end, you have a number. You can also put it, if you want, in 0 point, comma, whatever. No problem. How much is it? It's 291 divided by 5000, 00582, 0582 PL square. So it's more or less half of this value, which is 011, okay? So if this is the bending moment here it's smaller, in the middle it's a parabola, and it goes like this, okay? This value here is M maximum, okay? And it's written over there. Again, I put it in fraction in order to make the process clear. If you want, you can also rearrange it in this way. 0.0582 is okay. In the end, you will replace the numerical values to get bending moment values, okay? Last point of the first part is calculate the rotation at the right support, point C, clearly indicating its value as a function of P, L, and Ej, and sign clockwise or counterclockwise. Okay? Yeah. Speak up, please.
After the 29 over 100 is minus 29. I think it should be minus 21.
No, it's 29 at the first end. There is nothing concerning the second end. Okay, I need, you all have these values. More in detail, you will have the diagrams, you will check them, but keep in mind that we will have to design the longitudinal reinforcement at the bottom of the section, the point of maximum bending moment. So this value, which is over there, is relevant. Then the top of section B, so we will need the bending moment here, we know it. And then the spacing of the stirrups required at point A, so that value of the shear force over there, 29 over 50, is relevant, okay? This is, I'm saying it because I'm going to delete this, so you keep all the numbers in mind or available for later on. Last point is, as we mentioned, rotation at point C. Go back to the part of the structural analysis and look at what happens at point C. When we separated all the effects on the structure, you will see that rotation at point C, when you have x1 equal to 1, it's 0, correct? When only x1 is applied, the second span does not rotate, and so point C has no rotation. When we have x2 equal to 1, I will redraw what happens. You should have this drawing here. 1 here. And what I marked here are 4 arches. Your colleague asked me why 3 arches here. I explained. And then I draw here 4 arches. What was the value here? Remember, it was 4L divided by 3 times L divided by 6EJ, which I then worked out as 4L divided by 18EJ, which is 2L divided by 9EJ. Okay? Remember?
It is 1 over 6EJ, right? For it not to be common square.
What? Sorry, 1 over 6EJ. Yes, correct. L is here. So again, standard coefficient, not left, right, unloaded end, standard case L over 6EJ, not standard case where this is 4L divided by 3, 4L divided by 3 over 6EJ. The end is this. So now the question is, calculate the rotation at the right support, point C, clearly indicating its value as a function of P, L, and EJ, and sign clockwise or counterclockwise. Careful about the signs. This is a clockwise rotation, so with my calculations, now first I have to finish. What happens when the P when the load is applied, when load P is applied, rotation is equal to 0. So in the end, rotation at point C is what? 2L over 9EJ times, this value is for x2 equal to 1. Is x2 equal to 1? It's not. It's equal to, we'll look at it later on. So, is times x2, and what is the sign? This rotation is, you see it here, counterclockwise. Now we replace the number. 2L divided by 9EJ times, check the solution. What's this? X2?
3 divided by 100.
With what sign?
Minus.
Minus 3PL squared divided by 100, which means that in the end, what I have is 350 minus PL to the power of 3 divided by 150 EJ. What does this minus sign mean? Here, with these conventions, this formula gives a counterclockwise rotation. If I get a counterclockwise rotation with a negative value, it means it's clockwise. Clockwise.
Why do we know it's counterclockwise from the beginning?
Here, how is this rotation?
Okay.
With my x2 marked in this way, it's a counterclockwise rotation. Since x2 is negative, it becomes clockwise, as I guessed at the beginning. So the answer, in the end, to this, since I said and I wrote, clearly indicating its value as a function of PL and EJ, and sign clockwise or counterclockwise. The answer should be, value is PL to the power of 3 divided by 150 EJ without sign. A value is a value. And then you say clockwise. Okay? If you tell me it's a minus PL to the power of 3 divided by 150 counterclockwise, I'm not so sure that you understood. Okay? So when I say I want the sign, I don't mean minus or plus. I mean clockwise, counterclockwise. Let's take a short break, just 5 minutes, and then we'll go with the last 3 points which deal with the design part. As a matter of fact, I should say it's the easiest part. Okay, now to the second part, which is, as I said, is the design part, and it's the part where you have to introduce the numerical values. Up to this point, everything was done in the symbolic way, okay? P, L, E, J, whatever. Now, we have to replace the numerical values, and we have to start with the first request, which is design the longitudinal reinforcement at the bottom of the section at the point of maximum positive bending moment of span AB, assuming 12 millimeter diameter rebars. So we are at a point where the bending moment is positive. We have to design the longitudinal reinforcement. So it's a design task. How do we do that? Point E. So it's design reinforcement at M max. I will call it like this. First of all, what is the value of M max? In symbolic way, it was 291 over 5000 PL square, we have to replace the values. So P is 30 kilonewton over meter, load at ultimate limit states, and L is 6. So somebody do the math for me. 291 over 5,000 times 30 times 6 times 6. I will also do it, just to check. Can somebody do the calculation for me, please? Anybody? 0.05. Yeah. P is 30, L is 6.
62.64?
62?
0.64?
Well, I have 62.86, but it's okay. 62.86 kilonewton times meter. That's the unit of measure for bending moments. The assignment says design the reinforcement at the bottom. AS, I will mark it, even though it consists of rebars, I will mark it as a straight line. Remember, we are in a section where the bending moment is positive. Okay? So basically we have a tension force here and the compression force at the top. That's the situation. This is the section. This is the side view. What is the most important parameter when you design this? Remember from theory, we have this value, which is the internal lever arm. If I don't know the reinforcement, if I have to design the reinforcement, this value can be approximated as 0.9 D, where D is the effective depth. And as you see, it was given D in the section where the bending moment is positive and the reinforcement is at the bottom. D is equal to 35 centimeters. So we know that this is 0.9 times 35 centimeters. How much is this? Again, calculation, and check it please. 31.5 centimeters, which is 315 millimeters. Okay?
I have a question. The D is all the distance of the beam, but the D that
All the distance of the beam does not make sense.
the
Distance between the top fiber and the reinforcement at the bottom. It's marked. What D is?
it was complete, not until the reinforcements.
No. If you go back to the theory, you will see that we usually refer to this D, which is called effective depth, exactly because we don't care how much the total depth is. The only thing that matters is the distance between the top compression and the reinforcement. So this is an approximated expression of the internal lever arm. Then, what is the maximum force the unknown reinforcement can provide? We know it's the design yield strength FYD times S. So the maximum bending moment the reinforcement can provide is FYD times AS times internal lever arm. This is a general equation. How do we use it in design? In design, if this is the maximum moment the reinforcement can provide, I put this maximum moment equal to the design value, which is this one. So, in the end, and what do I design? FYD is known, it's a given. The internal lever arm, I just worked it out in an approximate fashion, so it's okay. The only design parameter is the area of the reinforcement. So, AS minimum, again, as we did last time, this is the bare minimum is this value here, M max, divided by FYD times times Z. In order not to mess it up with the units of measure, I strongly advise you to, first, transform the bending moment into Newton times millimeter, not kilonewton meter, but Newton millimeter, which means 62.86 times 10 to the power of 6 divided by FYD is given in megapascals, it's 350 megapascals. Now we know from the previous class and from what we did during the year, megapascals are equal to Newton over square millimeters. And then 315 is in millimeters right away. What is the result? Five, 7, 0, and the unit of measure is clearly square millimeters. It's an area. Okay? Now the design assignment read, design the longitudinal reinforcement assuming 12 millimeter diameter rebars. So the answer here should be number of rebars, not just the theoretical, the minimum area. I want a number of rebars. Okay? So what do I have to do? I have to divide this number by the area of one single 12 millimeter rebar. Okay? What is the area of, let me call it this way, A of a 12 millimeter rebar? P, Greek P, pi, 12 to the power of 2 divided by 4 equal, I should remember it by now, I still don't remember it. No. See, 113 square millimeters. Okay, one single 12 millimeter diameter rebar is 113 square millimeters, which means roughly 1 square centimeters. Makes sense, something like that. Okay, so this corresponds to 570 divided by 113 equal to, somebody do the math for me and check what I'm writing, divided by 113, 504. Bad luck. Just beyond 5. So to be safe in any case, even if it's very close to 504, since I'm not doing any additional calculations, I will have to round this up to 6. So A as provided is equal to 6 phi 12, which means 6 12 millimeter rebars. Okay? Do you get it? 5.04 is very close to 5. I could put here 5, but then I would have to do an additional calculation to check whether it's right. I could do it. Or if I simply stop here, this has to become 6. Okay? To be on the safe side. Are there questions about what I did here? Tell me. But speak up.
Let's say we do the maximum momentum, we put 62.8. So then it affects the actual value, and it's 500, let's say. would it be wrong, the question?
No.
Because of this
No.
application we made?
No.
Okay.
This is engineering, pharmacy school is on the other side of the road. So for me, 62.3 is equal to 62.86. Remember that we are not so sure about the precision of the gravity acceleration. I mean, somebody says 9806, somebody says 981. So if you have here 62.3 instead of 62.86, doesn't matter. You could also round it up to 63. Okay? Important thing, for example, for the evaluation of your written exam is this. Suppose you get this slightly more wrong than what he said. Basically, if you have 62.3 instead of my value, I consider it correct, okay? Once a guy came to me and asked me, could you do an expertise on my house which had a collapse? And I asked him, I'll explain a little bit more, and he told me, well, somebody opened up a hole in the wall and the building collapsed. I told him, if the difference is a hole in the wall, everything makes a difference. I mean, you open the door, the building collapses. You open the window, you move something, so the difference cannot be so small, which means if we have different small differences from the engineering point of view, it's acceptable, okay? It's within the tolerance of what we are thinking about, okay? But suppose here you have 50, okay? So you messed up, despite all my recommendations, you messed something up. Here you did something wrong in the calculations and you get 50. Now, if you do the calculations with 50, and from here on you are consistent, I will consider it to be right, okay? Of course, 50 is not so nice because it's not on the safe side. It would be better if you had here 70, okay? Wrong, but on the safe side. So again, don't mess the calculations up, please, okay? Other questions about this? Please focus on this fact. If it's a design assignment, we have to have an approximate value of the internal lever arm to do the calculations. So this is something you should remember. The approximate formula for the internal lever arm. I think I said during the course, if you have to learn something by heart, this you should learn by heart, because it's a very important rule. Okay? Second assignment says, check the longitudinal reinforcement at the top of section B, assuming it consists of 3 12mm diameter rebars. So, different assignment. F, check reinforcement at MB. Okay? Which means we know that at point B we have 3 12mm diameter rebars. We will also have stirrups. We'll have this. So this area here, AS, we know it's 3 phi 12. So the situation in this case is this. We have here MB. We worked it out previously. We have to check the longitudinal reinforcement. What does it mean to check the longitudinal reinforcement? It means answering the question, what is the maximum bending moment the assigned reinforcement can resist? And then ask yourself whether it is larger or lower than the applied bending moment. What is the applied bending moment? We know at MB, it used to be, remember, x2, unknown x2, 3 over 100 with the minus. Now we plot it in the right direction, so it's simply 3 divided by 100 p L square. What is the value? 3 over 100 pi L square. 003 times 30 times 36, 32.4. Okay? 32.4 kilonewtons meter. Now, in this case, what is the difference with the previous assignment? If you know everything, you don't do this approximate formula. Because you know how much the reinforcement is, you can accurately locate the compressed area and accurately evaluate the internal lever arm. How? Everything is given at the back of the page. Clearly, just to make it clear, the drawing is meant to represent a section subjected to positive bending moment. It was written. If it's a section subjected to negative bending moment, what changes? Compression is at the bottom, tension is at the top. So you simply look at the drawing in this way. Okay? And nothing changes. So, how does this section resist? Look at the drawing at the back. We have a compressed area at the bottom with a distribution of stresses which is based on the design compressive strength of concrete, FCD. We have the tension reinforcement at the top, which resists to FYD, which is the yield strength. So we have to work out first the neutral axis depth. The expression is given, so x equal to FYD times AS divided by 0.8 FCD times B, where B in this case is the width of the beam. Okay, also a given. Let's go with the values. Everything in megapascals and millimeters. So you get consistent units of measure and the final result which is in millimeters. FYD is 350. AS, 3 12mm diameter rebars. We worked out the area of 12mm diameter rebar previously, 113. So if it's 3 of them, it's 339. I will write it here. This is 3 phi 12. Then 0.8 is 0.8. FCD 20 megapascals. B 20 centimeters, which means 200 millimeters. How much is the neutral axis depth? Somebody do the math, please.
We do the calculation. Can you refresh my mind where we take the 20 of the FCD?
From the datum. See.
Okay,
How much is the result? 37. 37 millimeters. So this, the compressed area, not exactly the compressed area, but the neutral axis depth. As you see, there is a small difference due to this 0.8. We explained this in the theory part, is 37. If x is 37, how much is z? Z is d minus 0,4x equal to, how much is d? Again, d is given. In this case, since we are at a section with negative bending moment, look at the insert on the right. It's d prime, but d prime and d are the same. 35 centimeters, so 350 millimeters minus 0,4 times 37 equal to, my number says 335. Okay? How do I use this? Well, the equation I wrote previously for the design part is still valid if we do a check of the section. The only difference is, in this case, we know exactly how much the internal lever arm is. We don't have to do any approximation. So what are we going to write? We simply write the maximum bending moment, which is the resisting bending moment, given by this distribution is FYD times AS times Z. What are the numbers? Again, 350 times 339 times 335. All very much alike, but with different meaning. Yield strength, area, internal lever arm. I do the calculation. $350 times 339 times 335 divided by 1 million, because I want the result in kilonewton over meter. 39.75, let's say 39.8 kilonewton meter. The check should say section is okay, section is not okay. Is the section okay? Yes or no? Why? Because 39.8 is larger than 32.4. Okay? Quickly back to the previous assignment. Previously I said I could go with 5 rebars, but I would have to check it. What does that mean? If I choose in the previous assignment to do 5 rebars, then I would have to go through all this, and maybe with an accurate and more refined value of internal lever arm, I get a positive check. I leave this to you as a homework. Try to see with this formula here whether the point of maximum bending moment works with 5 rebars or not. Okay? And who wants can then show to me the numerical evaluations. Okay, when you're finished, I will erase the blackboard, and we are finally to the last assignment.
Ask a question.
Yeah.
Why are we using the V in the X formula? Because in the paper.
Oh, you're right, but this was mentioned when during the written exam. It was said out loud that there was a B missing.
Okay.
You see it also from the dimensions point of view. If you don't put a B, it's not the right dimension. Yeah, your colleague points to the fact that in the back of the formula, the neutral axis depth is missing the B. So it should read FYD times AS over 0.8 times the FCD times B. As I wrote it here. There is a B. Okay, last part. Design the spacing of the stirrup required at point A, assuming the stirrups consist of two-legged vertical 8 mm diameter rebars. Okay? So we know that when you have a section whatever section with stirrups, the maximum force it can bear is equal to FYD times ASW divided by S. This is the reinforcement, transverse reinforcement, multiplied by Z. Am I missing something? No. Okay, you should have this formula available in the theory part. We explained it. It comes from Ritter-Mersch-Strass. Okay, in its most simple approximation with compression struts all at 45 degrees. Okay, it's a safe equation if you design the reinforcement. There are other equations available, but we cannot go through all of them in a 4 credits course. So you have to be happy with this. Okay, it's safe anyway. So the important thing is to know all the things that go into the equation. First of all, FYD, no doubts about it. The design yield strength of the steel. In real applications, the yield strength of the stirrups may differ from the one of the longitudinal reinforcement, not in our case. ASW is the area of the transverse reinforcement, but you have to count it in a correct way. So since we have to take into account all the rebars which connect the top and the bottom in order to make sure that the beam works as a truss, this ASW is the number of legs of the stirrup from the top to the bottom multiplied by the area of the single stirrup SW4. Okay? This is the spacing, and this is the internal lever arm. Again, the one for bending. Now, we are at point A, to the left. Do we know the longitudinal reinforcement at point A? No. We designed it at midspan, in the first span, at point B. Point A we don't know, which means this one is 0.9D equal to, we worked it out previously, what was it? 315. Don't make me do it again. 315 millimeters. Okay? What is ASW? Number of legs times this. Number of legs is 2 times P divided by 4 times, what is the diameter of the stirrups? It's given 8 to the power of 2. This should be equal to what? 100 square millimeters. Let's do the calculation. 100 square millimeters. So as you see, we have this which is known, this which is known, this which is known, this is not known. I have to design it on the basis of what? Again, this is the maximum shear force the beam can provide. When I design it, I simply say VRD is equal to VAB, this value which I previously calculated. So this is the design condition, design equation. What is VAB? 29 over 50 PL Let's do the calculation just to check. I have the numbers here, but it's good to check every now and then. Times 30 times 6. 104.4, yes, that's it. 104.4 kilonewtons. How does this design equation become? I simply reverse, I bring S to the first member of the equation and VRD equal to VAB down. So S is equal to FYD times ASW times internal level arm divided by VAB. 350 times ASW in square millimeters, 100, times Z, 315, divided by the shear force, which I calculated in kilonewtons, should become newtons to make the units of measure consistent. Simply multiply it by 1000, so 104.4 times 10 to the power of 3. Let's do the calculations. So, 350 times 100 times 315 divided by result is 105.6, which means 106 millimeters. Previously, when I designed the area of the reinforcement, I said area, the minimum area, and then I rounded it up. What is this spacing here? Is it the minimum spacing or something else? In the case of stirrups, reducing the spacing leads to a higher shear force resisted by the beam. So this is not the minimum spacing, this is the maximum spacing. Which means, to be on the safe side, instead of rounding it up, I round it down. And how do I round it down? When you work with concrete, you don't go with millimeters, you go with centimeters. So this 106 becomes 10 centimeters. Nice number, neat number. The people on the working site will love you if you tell them 10 instead of 11. Okay? So this is the maximum spacing. The provided spacing will be equal to 10 centimeters. Okay? Again, when you round the numbers, you have to take into account of what you're doing, whether you're working at the pharmacy school with steel or with concrete, and also whether the quantity you're working with affects the safety in one way or the other. Previously, with the longitudinal reinforcement, the higher is the area, the higher is the resisting bending moment, so I round it up. Here, the lower is the spacing, the higher is the shear force resisted by the beam, so I round it down. So this is a maximum spacing, not a minimum spacing. Okay? Questions? Everything clear? Not possible. Statistically, not possible. Okay, now, first exam is on 11. I don't know if we still have time for another appointment. Because next week, yes. You maybe, yes. I don't know. So next week is like, so today is 22, 29. Then 29 means the next one is would be 29 plus 7 would be 6, so it will be the 5th of June. Okay, I will look for a classroom either on the 5th of June or on the 29th of May and let you know through the usual way where and what we're going to do, where we're going to meet and what we're going to do. Okay?